Assalamu alaikum dear students. I hope all of you are great and doing very well. This is your instructor for this class, Zeeshan Ali, and today we will be studying designing a one-way slab. So in previous classes we have studied about design of beams. I hope all of you have got a pretty good idea about that. So coming to one-way slab, what actually one-way slabs are, how are we going to design it? So think about it like this. One-way slab is actually like a wide beam. A wide beam of like 12 inches width, right? So that's how we are going to design it. A slab is considered like a one-way when its length to width ratio is equal to 2 or greater than 2. So when it's longer to shorter side ratio is equal to 2, that means that the slab will be one way, or if it's greater than 2, then it's going to be one way. But if it's less than 2, then that slab will be considered as two-way, right? So since you guys have studied about the beam design, so it's not really much different if we consider the simple beams. The design is going to be very much similar. The only difference is that the width is going to be 12 inches. Now if we look at this image, it's a very simply supported slab, right? With a pin support here and a roller support here. So now if you look, this slab we have considered only 1 feet width of strip, right? That's the strip that we are talking about, this, and that's the length of the slab, right? So we are going to be designing only this part, the length, however much that be, and the width of 12 inches, right? So that's the only basically the major difference when it comes to designing one-way slab. Now coming towards the differences in the design of beam and the design of slab, when we go very much into the depth of it. So now the first difference is that the thickness, when we determine the thickness of the beams as per the ACI code, it differs from when we calculate for the one-way slabs. Now if you look at this table 7.3.11, the minimum thickness of solid non-pre-stressed one-way slabs. Now looking at this table, the support conditions like simply supported, one end continuous, both end continuous, and cantilever. So the minimum thickness has been given for each condition. Like for simply supported, it is L by 20. Now for the beam, it was different. For the beam, it was L by 16, and here it is L by 20. So that's one major big difference. And the second difference is the rebars in the transverse direction are actually calculated as per the minimum area criteria, which is 0.0018 B times D. B is your width of the slab and B is your depth of the slab, right? So moving ahead, we will actually solve this question, example 4.6 of your book, Design of Reinforced Concrete by McCormack. I want you guys to please open your notebooks and start practicing as I explain this example to you, and pull up your calculators. So let's see the design a one-way slab for the inside of a building using a span, loads, and the data given in figure 4.8. Normal weight aggregate concrete is specified with a density of 145 pounds per cubic feet, right? So this is actually a simply supported slab, right? which has a 10 feet span, right? The live load is given. Live load is 200 pounds per square feet, and concrete compressive strength is given, which is 4000 psi, and steel yield strength is given, which is 60,000 psi, right? So let's write it out. As I have explained, the span is 10 feet, live load is 200 pounds per square foot. The density is 145 pounds per cubic feet, right? What we have to do is we have to use the ACI code provisions to design this one-way slab. Now design, what actually it means is that we need to determine its thickness, right? We know the span. We know that we have to design for the 12-inch strip, right? So what we need to do is determine the area of steel and the thickness of slab, right? That's what the design is. So getting into it, step one is minimum slab thickness, right? Now the minimum slab thickness as per ACI code for the simply supported slab was L by 20, right? You can go check out that table we just went over. So L over 20. So L, which is your right, which is your span, right, which is given as 10 feet. So what we have to do is we have to calculate L over 20. Now L is as your 10 feet divided by 20 gives us 6 inches, right? That has been converted to inches. As you know, 1 feet is equal to 12 inches, so we need to convert it here to inches, right? So 12 times 10, which gives us 120. Dividing it by 20 will give you 6 inches, right? I need you guys to please do it and practice it as we go forward. So let's decide slab depth as h is equal to 6 inches, right? That's how it's going to be. Now if we look at that, right, this was our support, 10 feet was our span, right? Now that 6 inches is our depth, or the complete depth of the slab, right, or height of the slab. So let's go ahead. Now stepping into the dead load, we have the thickness, we have calculated it as 6 inches, right? Unit weight of concrete is 150 pounds per cubic feet. You can actually, well, the given value is 145, but you can take it as 150. That is the normally used concrete density out there, right? But you can use 145 as well, so either of that value is correct. Now for the dead load, we need to multiply the depth of the slab with the density of the concrete. That's how we get the depth, the dead load over the slab surface area, right? So 6 inches was your slab, so divide the 6 inches with 12 to convert it into the foot. So you will get 75 pounds per square foot, right? I hope you guys got that, right? Getting into the step number 3, which is the total factored load. Now we need to apply the factors. Live load was given, which was 200 pounds per square foot. All you need to do is apply the load factors to your dead load and your live load, right? So the factor to the dead load is 1.2, you guys know that, and the live load is 1.6. Simply you need to multiply and then add these numbers and you will get 410 pounds per square foot. That's easy, right? Now getting to the step number 4, which is the strip load. Now again, what we need to find is the load that is distributed over the length of the slab, right? So what we need to do is multiply that 410 pounds per square foot that we got with 12 inches, right? So that's how we will get the load that is spanned over the length, right? Which is 10 feet. So WU will be equal to 410 pound per square foot multiplied by 1 feet, which gives you like 410 pounds per foot, right? So that's actually your load that is on that is carried on your slab, right? Now what you need to find is factored moment, right? For simply supported slab, the moment is actually WUL square divided by 8. Now, how exactly did we get this value? What you need to do is find the shear force and the bending moment of your slab, that is simply supported slab. Now, after doing that, you will be able to find how we actually got that value, right? So what you have here is, I want you guys to do it on your own. Simply draw a simply supported beam, right? You have a uniform. I've made a mess of that. Let me redraw. It's simple, like you need to simply just draw a simple beam, right? And which actually carries like load of 410 pounds per feet of uniform load, right? Now if you calculate it, you will get a shear force diagram like this, right? And a bending moment diagram like this. Now what the value in which you're basically interested is this value, right? So the formula after calculating all of this, what you will get is WUL squared by 8, right? L is your span and WU is what we just calculated as 410. Now after doing all this calculation, you will get your required moment. The moment that you have to design for is 5.125 kip foot. Okay, let's move forward. Now the sixth step, you need to find reinforcement ratio. Now for reinforcement ratio, you need effective depth, which is approximately equals to 5 inches, right? So this is your slab, right, which is equal to 6 inches. We said that that's the height of our slab. Now what exactly is the depth? The depth is actually your height of slab subtracted with or the height of this slab from top till your bars, right? Till the half of your bars. So let's say my bars are here. It's just assumption for right now. So the height from the half of your bar to the top of your section, that will be your depth of slab, right? So you can calculate it here 5 inches. So let's say height was 6 inches, and let's say I'm using bar number 4 number bar, right? So for 4 number bar, the die of its die is actually 0.5, right? So 0.5 divided by 2, right, minus the clear cover, right? There has to be a clear cover as well, which is 0.75, right? Now if you calculate that, you will get 5 inches, right? So the next step that you need to do is you need to calculate the value of mu divided by 5bd square. Right now, if you get when you get this value, you can check the appendix table A13 from the book, and you will automatically get the value of rho, which is your reinforcement ratio. Right, after doing that step, we actually got 227.8 psi. All right, so let's go to this table. Now if you look into the table, the value that we got was 227, right? But we only have like 225.9 and 231.5 psi. So for 225 it's 0.0039, and for 231 it's 0.004, right? So it lies somewhere in between 0.0039 and 40. What you need to do is do some mathematical interpolation. After interpolation, you will find that the value that you got was 0.00393, right? I want you guys to do that and show it to me in next class, right? So and the next condition is the rho minimum, right? Rho minimum is your 0.0333, right? Which classifies as the condition is okay. Now where did we get that? You actually go to table A7 of your book, and you go to the grade 60 steel, right? And there you will find for the 4000 psi and for beta 1 as 0.85, the rho minimum is 0.033, right? So the condition is satisfied, right? uh, in case your area of steel was lesser than the rho minimum, then you would have to use the rho minimum value, right? But now that the area of steel or the rho value is actually greater than the rho minimum, so you need to use the rho value, right? Now I hope you guys got that, right? Rho minimum is 0.0033 and rho value is 0.00393. all right, let's go ahead. Now getting to the step number 7, we need to find the required steel area. Now the steel area, its formula is rho BD, right? So you guys got the value rho, which was 0.0393. After calculating it, you'll get 0.236 inch square feet, right? So we can use bar number 3 as well. You can use number 4, you can use number 5, but with all these conditions the spacing will change. So again, you need to use the bar which suits your condition very well, right? So here we will use this bar number 4, and its area is 0.196 inch square per feet, right? You guys know how to calculate the area. It's simple. What you need to do is calculate the diameter of your number 4 bar. So for number 4, you need to divide it by 8. You will get 0.5, right? So when the diameter is 0.5, what you need to do is find the cross-sectional area. And the cross-sectional area, how you will calculate it? It's simple. You need to use the area of circle, which is pi d square divided by 4. That's how you will get 0.196 inch square per feet, right? Now for spacing, what you need to do is you need to use the formula AB over AS, or AB divided by AS multiplied as whole by 12, right? So when you do that, you'll get 9.96 inches. So you can provide bar number 4 at 10 inches center to center spacing, right? That's your main steel bars, right? That's what you need to lay on your slab. Now coming toward the shrinkage and temperature steel, which is actually are your bars which are perpendicular to your main steel bars. And it's simple. The ACI simply gives us a simple formula for the minimum area of steel, 0.0018 BD. So the area required is 0.1296. Now again, here you don't need to actually use a whole lot of bars, heavier bars. You can use bar number 3 at 10 inches center to center spacing. Now center to center spacing is simple to calculate. You need to simply use the formula AB over AS multiplied by 12, right? So that's your temperature and shrinkage steel, right? So final reinforcement layout, we need to now sum it out. The main flexural steel we got was number 4 bars at 10 inches, and the transverse bars were number 3 at 10 inches, and the spacing is actually less than 18 inches, so that's okay. ACI actually requires you to keep a maximum of 18 inches, so ours is 10 inches, which is fine, right? So here's the final summary. Your slab thickness was 6 inches, your factored load was 410 pounds per square feet, your factored moment was 5.125 feet kip feet, and your flexural reinforcement was number 4 at 10 inches, and your shrinkage and temperature reinforcement was number 3 at 10 inches. All right, I hope you all got that. I think it's enough for today. If you haven't gotten any understanding, or you are confused in any step, you guys can reach out, and I will always be available to help you out, to make you understand, right? That's what I'm here for. So okay guys, have a good luck, and please study hard, and good luck for your future. All right, thank you.